Hello, I'm Michael Woods, Chief Scientist at the Asian Turfgrass Center. I gave this presentation in Manchester, England earlier this week at the European Turfgrass Society conference, and the session chair, Bernd Leinauer from New Mexico State University, he introduced me as one of the most controversial turfgrass scientists today. And it seems to be that I'm controversial, he said, because of the very thing that I'm going to talk about. Now, in this presentation, I think I'll show you that maybe it's not so controversial after all. It's pretty logical what I would like to share. This one, I think, is not controversial. We can all agree about it, that the objective of turfgrass fertilizer applications is, at a very basic level, to ensure that the turf is supplied with just what it requires, and at the same time avoiding or minimizing over-application. Now, to do that, it sounds like a pretty simple goal and a pretty simple thing to do, but it turns out that it's trickier than you might think. And we want to do this for all kinds of turf. So whether, starting from top left, we've got fescue turf, a links golfing surface at Carnoustie in Scotland. At right, we've got a lower maintenance turf, a lawn. This happens to be Manila grass in front of a palace in Mysore, India. And we've got a grass tennis court, also of Manila grass. This is in Shizuoka, Japan. And then at left, a lawn in Florence, Italy. For all of these turf surfaces, there's a different type of surface that needs to be produced. And as far as fertilizer goes, the objective is to supply the grass with all it can use and to avoid over-application. In today's presentation, I'm going to outline or give a short history of this problem. And you might not have realized that there's a problem with turfgrass fertilizer recommendations. I'll explain what that is. And then I'm going to give two solutions. At the end, I'm going to give two recent and general solutions that I think solve this problem and give us an excellent framework to work from moving forward to do even better with turfgrass fertilizer recommendations. First, for the history, let's go back to 47 years ago. And this is a quote from a textbook by John Madison from Principles of Turfgrass Culture. If we turn to page 270, he says, fertilizer is the number one management tool. It is worth all the attention you can give it. And fertilizer is really important because it changes the way the grass looks, and especially it changes how fast the grass grows. So for any of those surfaces, for any kind of surface that we are trying to produce, it's really important to adjust the growth rate to be just what we want, or as close to what we want as possible. And also we want the grass to look and have the type of color that we want also. And fertilizer plays a really important role in that. And if there's not enough nutrients, the grass won't be as vigorous or as healthy as we would like. So that could be problematic also. So this is something that's worth all the attention that it can get. And in this presentation, we'll talk about how we can do that. We'll go to 40 years ago now and start talking about turfgrass fertilizer recommendations. There's a really interesting article by Tom Turner and Donald Waddington from 1978. They did a survey of soil testing programs for turfgrasses, and they sent samples to different laboratories, and they wanted to find out what were the differences in fertilizer recommendations for turfgrass maintenance and establishment. And there's a quote from that paper that as they studied this, and now the highlights are mine, the text in orange is something that I've highlighted. But as they studied this, here's what they found. They said, unfortunately, turfgrass recommendations appear to be based on research done with other crops, such as forages, results from turfgrass fertility studies that were not designed to relate to soil testing, and also on the best judgment of the agronomist making the recommendations. So that was the situation clearly identified 40 years ago. And since then, there's been an explosion or a proliferation of turfgrass research, all kinds of of new scientists, all kinds of experiments done, all kinds of graduate students working on various things related to turfgrass. So you might think that in the past 40 years, we would make progress in solving some of those problems that were identified 40 years ago. So I'm going to take a quote now from a book that was published 17 years ago. And this book is called Turfgrass, Soil Fertility and Chemical Problems. It's by Dr. Carroll, also Dr. Waddington, who is one of the authors on that paper from 40 years ago, and Paul Reiki. If we turn to page 164 in that book, we can read this quote. Turf grasses have been placed in a high phosphorus and potassium requirement category. This decision was based on economics, not agronomics. The cost of fertilization was not considered of primary importance for turf. So leading up to, or continuing on this timeline up to 17 years ago, this problem was still existing. And I'm going to now look at a couple quotes from 5 years ago from some reviews. And you would think that by 5 years ago, surely these issues have been resolved, or at least some progress would be made on this. This is now from Kevin Frank and Elizabeth Gertall, and this is from the recent Turfgrass monograph. Speaking of phosphorus, calibration of soil phosphorus with turfgrass growth and subsequent phosphorus fertilization recommendations is scant, and additional data is needed. Many current recommendations for pea fertilizer for turf grasses are based on forage or field crop calibration data, which is exactly the same situation that we were in 1978. Okay. Seems that progress isn't happening quite like I would expect. Here for potassium, relationships between extracted soil potassium, potassium fertilization rates, and turfgrass response needs additional study. Such work is especially missing for the sand-based systems in which many turf grasses are managed. So it turns out that there's this long-standing problem that's not really been addressed yet with turfgrass fertilizer recommendations based on soil tests, which is the way it's typically done. And that's a problem that's been identified since the 1970s. Up to now, it's not been solved. And I'm going to explain something that I think makes this an especially challenging problem to solve in the traditional way. Here we can look at festuca in Iceland. This is fine fescue growing in a particular soil, being managed to produce a particular type of surface, and it's in a particular climate. So we have that combination, and we can move to another part of Europe. This is zoysia grass in the American Military Cemetery near Florence. Now we have a different species of grass. It's growing in a different soil. It's growing in a different climate, and it's also being managed to produce a cemetery lawn, not a link-style golf course putting green. We can go to another part of Europe. Now we're in the Algarve in Portugal. Now here we have 3 different grass species growing on this golf course. There's agrostis, cynodon, and festuca, tall fescue in the roughs there. Here we have different soils, we have different climate, we have different species, and we have a different type of surface produced here. And here in the Pyrenees in France, this is primarily a Poa annua turf. It's growing in a different soil, different climate, different grass. But for all of these situations, we're supposed to come up with a way to make a fertilizer recommendation that's going to meet those requirements of supplying the grass with all that it can use, or supply the grass with all that it needs, and at the same time minimizing over-application or unnecessary application of nutrients. And I want to suggest that the reality is conventional soil test calibration will never be done for even a fraction of the turf species, soil, and climate combinations. The problem that's been outlined since 1978, and the problem that keeps coming up in the traditional research or the traditional way of looking at this is that we don't know for a particular soil and a particular grass combination in a particular climate just how we can interpret the soil test. That's essentially what the problem is. But because there's so many different grasses grown around the world, so many different management styles, so many different types of surfaces that are produced, so many different soils and climates that the grasses are growing in, I would suggest that we are never, ever going to do that type of soil test calibration. If we go to the part of the world that I primarily work in Asia, this problem becomes even more pronounced. And also, I think the reality becomes even more pronounced that this work will never be done. This is Poa pratensis. Now we're looking at another grass species. This is on a soccer field. This is at Kashima Soccer Stadium in Japan, a bit east of Tokyo. This grass receives about 400 kilograms of 400 kilograms of nitrogen per hectare per year. So it's growing very rapidly. It's producing a beautiful surface. How do we make fertilizer recommendations for this grass, this soil, this climate with that amount of nitrogen applied? How do we make sure it has enough phosphorus and potassium? I don't think we're going to do site-specific calibration for that. And then we can go to Thailand. Now we've got another grass species. This is Seashore paspalum. This is at the SCG Stadium, a little bit north of Bangkok. And now we've got another grass growing in another soil, in another climate. How do we make fertilizer recommendations for it? Here's pearl grass in Bali. Different soil, different grass species altogether. This is at the Nuara Elia golf course. This is Digitaria didactyla or blue cooch. Nuara Elia is in the highlands of Sri Lanka. It's at an elevation of more than 1,800 meters. This is where the best tea in the world is grown. There's a lovely golf course there growing in a different soil, different climate, different grass. The traditional way of doing soil test calibration, of saying we need to have data that's specific to this grass and specific to this soil, I say the reality is it's never going to happen. But I would still like to be able to make a fertilizer recommendation for every one of these places and for every other place also that meets the rule of supplying the grass or meets the objective of supplying the grass with all that it can use and at the same time minimizing over application. I'm going to change now from describing the problem to giving two recent solutions, explaining what these are. And I think that both of these work well. Although I prefer to do this actually with soil test data. So first, let's consider what we would do if we don't have soil test data, because we can actually solve this problem in one way to solve this problem and give a good answer is to make fertilizer recommendations without soil test data at all. And then my preference is to do it with soil test data, so I'll explain how that works. If we don't have soil test data, in this case, it makes sense to me to apply, at least initially, all that the plant can use. So we make the assumption that the soil can supply nothing because we don't have any data from the soil. So to be risk averse, to make sure that our high quality managed turf is supplied with all it can use, we want to supply all that the grass can use. And this is exactly the STERF precision fertilization approach. You can download this excellent document by Erickson et al., Precision Fertilization from Theory to Practice. This document is available on the STERF website, and this explains the background behind this and how to practically apply it. A couple quotes from that document. It says, precision fertilization is based on the assumption that during vegetative growth, grass requires nutrients in constant relative proportions. So one finds what those proportions are, and then based on how much the grass is growing, one supplies those nutrients. It's essentially saying the grass is going to grow based on how much nitrogen is available to the grass, and the amount of nitrogen sets an upper limit on how much the grass can grow. And based on that, we know, based on those constant relative proportions, we know how much potassium, phosphorus, magnesium, and so on need to be supplied to the grass. It just ignores the soil and says, as the grass is growing, we're going to feed it with the nutrients that it's using. It's a very simple approach. By matching fertilization to requirements during the season, it is possible to avoid undesirable fluctuations in grass growth and playing quality. So one is essentially providing a steady stream of nutrients to the plant that is in proportion to the plant requirements and in proportion to the growth rate of the grass. However, that completely ignores the soil, and it doesn't make sense to apply all of those nutrients if the soil can supply those nutrients. And this goes back to a quote that I often remember from Wayne Cousteau, a professor from the University of Wisconsin who just died last autumn. And he has a tremendous amount of wisdom in this area. And his articles, if you read them, have tremendous advice that I think maybe I've thought of this, and then I'll read it and say, wait, Wayne who thought of that and wrote about it very clearly some time ago. So there's an article, I think he was writing about fertilization of creeping bentgrass, and he wrote, how many more times do I have to say that adding nutrients to a soil that's already well supplied with those nutrients is a waste of time and money? So if we can look at the soil and find out if the soil can supply those nutrients, then we can refine that precision fertilization approach and supply the nutrients in proportion to how they're used by the grass and at the time of the year when they're used by the grass. But if the soil already has enough, then we don't worry about it. So in this case, we want to ensure the grass is supplied with all that it can use. But if the soil can supply some or all of that amount, then the fertilizer recommendation needs to account for the soil supply. I'm going to talk about the minimum levels for sustainable nutrition, or MLSN, and this is something that was developed by me and by Wendy Galernter and Larry Stoll of PACE Turf. And this is a project that we started in 2012. We realized that we had, between ATC and PACE Turf, we had a large collection of soil samples where we had soil test data that were collected from good performing turf. And from those, we didn't want to look at those with a really low pH. We didn't want to look at those with a really high pH, because in those cases, we actually would recommend to adjust the pH before doing something else. So we just looked at those with medium pH. And then we wanted to look at those only with a relatively low nutrient holding capacity, something similar to what Kevin Frank and Elizabeth Gertall wrote about the types of soils that turfgrass is commonly grown in today. Those low cation exchange capacity sandy soils, or turf that's top dressed with sand, will tend to be growing in a low CEC soil. And we also make the assumption, of course, when we're doing this, that if good quality grass can be produced in a soil with relatively low nutrient content, then a soil that has a lot more nutrients than that will obviously be well supplied with that. So we just want to focus on the low end, because that's where the problems are going to be. Having too much potassium, too much calcium, too much magnesium is not a problem. And we've written about this. The most detailed exposition of this you can read about in PeerJ preprints. This is what the data looks like for potassium. And we work with the Mehlich 3 soil test here in this project. So all of these tests were done by Mehlich 3. And this is a histogram showing the distribution of potassium for all 16,163 samples. After we do the filter and take it down to 3,683, so these are the low CEC soils and with a pH from 5.5 to 8.5. This is the distribution of potassium by Mehlich 3 in those samples. And this shows what the conventional SLAN, or sufficiency level of available nutrients guideline, is. This is 117 parts per million. That's that vertical line. So with that vertical line, 82% of the samples in the MLSN database are below 117 parts per million. So 82% of the soils from good performing turf would be classified by conventional guidelines as requiring more potassium fertilizer and would be recommended potassium fertilizer. So this essentially demonstrates what the problem is there's good performing turf all over the world that is getting recommended fertilizer because the conventional guidelines are not appropriate. And that's because of the problems that I outlined. Calibrations done with different crops, research done that wasn't related to or wasn't designed to relate to soil testing, things done based on the best judgment of the agronomist making the recommendations, and so on. So we wanted to say, let's look at the reality. What are the soils that turf is growing in, and how can we make recommendations based on the reality of good grass today? This is the phosphorus data from the MLSN data set. If we look at the phosphorus data from the MLSN data set, 52% of the soils would be recommended phosphorus fertilizer, because the conventional SLAN guideline says if you are less than 55 parts per million or milligrams per kilogram, that's the same thing, 55 milligrams per kilogram phosphorus by the Malic 3 extractant, you've got a 50% chance of getting an immediate turfgrass response and a very high likelihood of seeing a response by the end of the season, or seeing the grass condition deteriorate by the end of the season if you don't apply it. That's what the conventional guideline says. But there's good performing turf at 10 parts per million, 15 parts per million, 20 parts per million, 25 parts per million. So we don't think that 52% of good performing turf soils need additional phosphorus fertilizer. So what we did with this project, we took those distributions. We looked at what the distribution of the nutrients were, and then we fit a probability distribution to those, and we found that a 2-parameter log logistic distribution fits these well. And because they're not distributed normally, most of the density is concentrated closer to zero. It's concentrated relatively low on the horizontal scale, on the horizontal axis of how much of a nutrient is in the soil. But for some soils, there's a very long tail. There's some values of potassium that are quite high. There's some values of phosphorus that are quite high, but most of the soils have nutrient levels that are relatively low. So we can't use a normal distribution. So we used a 2-parameter log logistic distribution. And from that, we can get a cumulative distribution function, which looks like this. So we can look at any level of the nutrient in the soil or any level of the soil test result and find out what the probability is that the value in that distribution that the other samples in that distribution would be below or above that particular value. So for the MLSN minimum, this is illustrated pretty well in the Turf SI Shiny app, and the SI stands for Sustainability Index. And this is something that you can find on the Asian Turfgrass website. This is something where you can put in your own soil test result from the Malic 3 extractant, or take your soil test data, convert it to estimated Malic 3, and then use this. And you can see where the result would be compared to the MLSN data. Now, on these charts on the right, these show the cumulative distribution function, where each of these values are set at the MLSN minimum of 0.1. So if the soil test potassium is 37 parts per million, then the cumulative distribution function here would be 0.1, or the probability of a value being less than or equal to 37 would be 0.1. So essentially what we do is just say, don't be below this. 10% of the samples approximately would be below that. But if you're at that level or above, you will be fine. You will be well supplied with that nutrient. So based on this approach, we can make fertilizer recommendations that still have a safety buffer, because we know that good turf is produced below this level, but we don't really want to flirt with the possibility of a deficiency. So we just kind of throw away that bottom 10% and say, stay above that. If you make your fertilizer recommendations to stay above that, we are confident that you will have plenty of nutrients, and then the grass will be supplied with all that it can use, and at the same time will be minimizing any over application or unnecessary application of fertilizer. That's all there is to it. For more about this and other turfgrass issues, you can see plenty at my website, asianturfgrass.com, or if you like a steady stream of turfgrass information, please follow at Asian Turfgrass on Twitter. Thank you.